a physicist can choose to indicate this by creating a fewer digit version of this number using scientific notation. Step 1, insert a decimal somewhere into this mess to create a number between 1 or greater than or equal to 1 but less than 10. Okay? Greater than or equal to 1 but less than 10. Okay? I'll be right it that way. All right, so it can be between 1, but including 1, and 10, smaller than. Okay? If I were to graph that on a number line, it would look like this, just to kind of help you. It can include 1, but it cannot include 10. These are the numbers we're going to create. And I would plug in my decimal between the two ones, creating 1.18. 1.18. Now, in order to explain to the person you're communicating with what this is, though, it's not 1.18, it's 118 trillion kilometers. So rather than writing 369 zeros, we can simply indicate how many positions to the right this decimal must be moved to actually be the real number. This is the representation, this is the real number. So if I were to count, it would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay? And that's what they have written there in that first slot. Okay? That first slot actually shows the maneuvering of this number. 1.18 times 10 to the 11th would be the scientific notation of that number. It requires less ink to write that. They give you another example for 4,709,000,000. Here's another one, 4,709,000,000. This is the other one. This, I don't know what it represents, but it's a big number. Where would I insert the decimal to create a number greater than or equal to 1 but less than 10, Grace? Since you were absent yesterday. Yep. Okay. 4.709. So I've placed my decimal, and now I need to tell the person what number of positions this decimal is away from its original spot, which is 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the scientific notation representation of that number. Okay. Teeny weeny numbers also fit. Why would anybody want to write as many zeros as you see in the diameter of a silver atom? I can't even imagine why you'd want to write that. So 0.00, shoot, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, yeah, 2, 4, 6, 8, 10, 12. This is the diameter of a silver atom. In case you want to know, entertain your friends. Okay, first, insert the decimal between a number to create something that represents that scenario. We did that. .5. Now what makes this different is we're not going to have a positive exponent anymore. It is now negative, because to return this to that, the decimal is getting moved to the left. Notice these, the decimal goes right to go back to normal. In this, the decimal has to go left to go back to normal. For that scenario, it's a negative exponent. And if you count the number of positions it would take to return 2.5 to this monstrous number, you would find that it is 13 spots. Okay? You guys with me on that? So it is a negative 13. Okay? Negative 13. So 2.5, you might have too many zeros too. You
Yeah.
can't even visually see that many zeros. Example 1. You guys see example 1? We've got a big monstrous number, 58, 120, 6 zeros. Okay, this is example A. I'm going to insert my decimal. Where, Seth?
Right after the 5.
Yep. That will indeed create a number that fits this scenario. And you have to write all of the digits that are significant. In other words, these digits here are really only placeholders, because without them you'd have 5,812. Okay? So I don't need to write any more zeros. I mean, that's the whole point of using this, really, from an elementary standpoint. Anyways, you only write the digits that represent value. Notice I could not wipe this one out because this one's a placeholder. Okay? So anything that has a value or is a placeholder between two numbers with value has to be written. Anyway, 5.812, is it going to be a positive or a negative exponent? Positive, because it's a big number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 to the 10th? Good. All right, B, a teeny weeny number. Jimmy Creamy, 1, 2, 3, 4, 5, 6 zeros. 0.0000072. Okay. My red dot is going to go where, Jared? Good. This is the easy part of all this. 7.2 times 10 to the negative or positive?
Negative.
Negative. 7?
Yep.
Okay. This is the easy stuff. Example 2 is also quite easy. It's what if you have scientific notation and you are told to write it in decimal form. They mean standard form. Okay, what they're saying there is create a scenario where it's not scientific anymore. Okay, decimal form is basically what you would think of as standard form. Okay, how you write normal numbers. All right, A is 4.95 times 10 to the 8th. I'm going to show you how I do these. 495. Okay. 1, 2. How many more zeros do I have to add to get up to 8? 6 more. 1, 2, 3, 4, 5, 6. Okay, did you guys see what I did? I'll show you one more time. Here's 4.95. 1, 2. That gets me to the end of 4.95. In order to move 8 positions, I've already moved 2. I need to move 6 more, so I'm going to need placeholders to make that happen. There's your answer. And B, a teeny weeny number, 7.63 times 10 to the negative 5. Okay, I am going to leave space to the left of the number because I know that from here, I'm moving that way. Okay, so rather than write it here and then not have any room, I left space in front of it because I know I'm going to be inserting some zeros. So 1 gets us to the end of the normal numbers, 2, 3, 4, 5, and there is your answer. Okay? These two techniques okay so far? All right. Example 3. Yesterday we revisited dividing where bases are the same, but you have exponents. That's going to come into play today. Here's A. This is example 3. 3.2 times 10 to the 7th divided by 2.0 times 10 to the 4th. You might want to plug this into your calculator and come up with some answer, and you could do that. But the more effective way of doing this is to separate right here and say 3.2 divided by 2 multiplied by the quotient of 10 to the 7th divided by 10 to the 4th. Okay? I can do this in my head. Did you come up with 1.6? If you think 32 divided by 2, that's 16. So 3.2 divided by 2 is 1.6. Now, remembering again, if you're dividing with the same bases, you simply subtract your exponents. 7 minus 4 is 3. There's your answer to this division problem. Okay? Separate it into 2 chunks. Divide each piece, and you have your answer. Now, if they said write your answers in decimal form, obviously you'd then, think, well, I could have used my calculator, or okay, it's going to be 1600. Great. But they didn't. They said write them in scientific form, so you might as well just divide it in scientific form as well. Multiplying also works quite conveniently. 2.5 times 10 to the 3rd times 6.0 times 10 to the 2nd. Okay. Multiplication, if you recall, can be done in any order. Okay? Lucky for us, we've learned that already. We learned that we can commute numbers and multiply them in any order we choose. So I am going to commute my normal numbers together. Okay? And I am then going to multiply those. And whatever their product gets multiplied by the product of these guys. Because think about it. What this long sentence says is 2.5 times 10 to the 3rd times 6.0 times 10 to the 2nd. Okay? So by rearranging this mess, it makes it more easy for me to visualize the answers. I can do this in my head. 6 times 2 is 12. A half of 6 is 3. So you should have come up with a 15 there. Multiplying exponents with the same base, you simply multiply them together. Or add them together, I'm sorry. You should have something that looks like that. Am I right? Am I done? No. Because of the previous page where I had the number line drawn, while this is scientific notation of sorts, it's not proper. Okay, currently the decimal is sitting here. I need it to be a number from 1 up, but less than 10. So by placing it here, I have now changed my exponent, and I have a proper scientific notation answer. So this here would be marked wrong because it's not proper. Technically, it allows you to say the same thing, but it is not correct for scientific notation. Same goes for C. If they tell you 0.4 times 10 to the 6th, I'm going to say, well, there's something wrong here. There's something wrong here. You have a number that is too small. Okay, and they kind of break it up for you, but I'm not going to do that. I'm just going to show you that if I move this here, I now have 4. And in order to return it to whatever its original value was, I only have to move it 5 positions now. Another way you could think of this, if this bothers you, because for me it's a little bit confusing, I usually take this 0.4 and make it the original version, 4, 2, 3, 4, 5. Okay? So what this is represents this, albeit incorrectly. Okay? So I go back to this, and I now convert this by putting in my decimal and counting how many positions it would go to be the correct version. Okay? So if you're given something that's incorrect, oftentimes it's easiest to figure out what it's representing, and what it is representing here is 40,000. Once I figured out that it's representing 40,000, I inserted my decimal, and counted 5 positions to create the proper scientific notation. This is quite useful in science. I've already shared that with you. But in order to do the science, you have to be able to do the math. So let's look at example 4, where it says, the distance from the sun to Mercury is approximately 6 times 10 to the 8th. So sun, Mercury, and I'll put Pluto out here, our little non-planet planet. So from sun to Mercury is 6 times 10 to the 8th. The distance from the sun to Pluto is 5.9 times 10 to the, lost my place, 9th. Find the ratio of the first distance to the second distance. If you are given 2 pieces of information and they say to find the ratio, it is a division problem. And rather than give a decimal answer, you're going to give a fraction because they're asking you to find the ratio. Okay? Ratio of Saturn to Mercury versus ratio of, or distance, I'm sorry, distance of Saturn to Mercury over distance of Sun to Pluto. Sun to Mercury, Sun to Pluto. That'll give you the ratio of their distances. So we start with our little guy. 6 times 10 to the 8th over our big trip. 5.9 times 10 to the 9th. Back up here, I shared with you when you have a division problem involving scientific notation, it's easiest to separate, like we did here, and perform the division separately. These 2 pieces created that. Subtracting exponents with the same base creates that. So 6 divided by 5.9, isn't that convenient? And 10 to the 8th divided by 10 to the 9th. Okay, this is really an odd one. Don't mess with this just yet. If I look at this, I get a -1, right? 10 to the -1. And if I just ignore this for the time being, I have this. They're looking for a ratio, which is a fraction. So rather than divide this, somehow I want this to be an answer in fraction form. Well, what is 10 to the -1st in normal fraction number? 1 over 10. So 6 over 5.9 times 1 over 10 equals, I ran out of room here, 6 over 59. Okay? So I went from here to here, up to here to solve it. Because I was looking for a ratio. Okay, I didn't need a decimal equivalent of this. They wanted a ratio. So to make this somehow represent a ratio, I needed to keep it in fraction form. So if I take this and multiply it by 1/10, the fractional representation of this negative exponent, I get a fraction. So the ratio is 6 to 59. So what a huge difference. So like say for every 6 miles Mercury is from the sun, Pluto is 59. So a huge, huge, huge distance. Okay. Example 5. This reminds me of you guys' 3rd, 4th, 5th grade books, or stuff. Write each number in expanded notation using powers of 10. Using powers of 10, 8,572. So you guys used to do 8,000 plus 500 plus 70 plus 2. I don't know if you guys remember that. But if I want to write 8,000 third grade style real quick. If I want to take this and break it up into expanded notation using powers of 10, that is like taking this and saying 8 times 10 to the third, added to 5 times 10 to the second, added to 7 times 10 to the first, added to 2 times 10 to the 0. Remember, anything to the 0 is 1. Not done yet. Oh, yes, I am. Jeez. Here's your answer. They just wrote it with dots. Numbers that are teeny-weeny, like example B, are a little tougher, but you can definitely figure it out. 3, 9.
I need Kyle Gray, Emma Jovine, and Clark Davis to come to the office, please.
Okay. Point 3 is in the 10th position, right? And a 10th is 10 to the negative first. The 9 is in the hundredths. The 9 is in the hundredths position. If that's a 10th, what do you think a hundredth is going to be? Negative 2. The 4 is in the thousandths position. So what do you think it's going to be? And continuing the 6th. Okay, because 10 to the negative 1 is 1/10. 10 to the negative 2 is 1/100th. 10 to the negative 3. You could probably keep going from there, right? And remember, you learned that to write this without using negative exponents, it's 1 over 10 to the first, which is 1/10. 1 over 10 to the second, 1 over 10 to the third. And all of those things can be solved. Okay, example 6. Finally, example 6. If you wanted to equate numbers with other numbers, but you don't want to write all the stinking zeros, you can use powers of 10. Not that you necessarily would for things that are this simple, but you could. Now, normally you would tell me 1 kilometer is 1,000 meters, right? Would you agree? Let's write that using a power of 10. 10 to the what is 1,000? Third, good. And normally you would tell me that 1 milliliter is 1,000th of a liter. Put another way, there's 1,000 milliliters in a liter. Okay. Instead of writing this way, you can write it as a negative exponent, 10 to the negative. Right. Bravo, mi amigos. Okay. I would like you guys to practice a few of the orals before you actually start your assignment.